FPGA fault injection is a well-known verification technique. It has many applications in FPGA prototyping, including robustness evaluation, verification of a system behavior in presence of faults, identification of safety and security vulnerabilities, and also testing fault tolerance and safety mechanisms. In modern FPGAs, faults can be injected by manipulating the content of configuration memory. This method is known as runtime reconfiguration. Most fault injection tools implement this method in one way or another, and to be useful in most of these applications, these tools have to somehow identify irrelevant configuration bits that should be targeted to emulate faults in individual design components. Unfortunately, the modern design automation tools do not report which configuration bits are used by each component in the design tree. For this reason, many fault injection tools rely on the black box approach. Its idea is basically to blindly sample essential bits. Essential bits, in the Xilinx terminology, is a subset of configuration bits that determine the circuitry in FPGA. So only injection in essential bits may have any potential effect on the design behavior. Location of these essential bits is reported by Xilinx Vivado tool when generating the bit stream. The problem of this approach is that it does not provide any visibility of individual design components. As such, this approach is useful mostly for the robustness evaluation. Some tools follow more refined gray box approach. Its idea is to isolate the targeted design component in a dedicated chip area, or P block. With the basic knowledge of bitstream composition, we then can locate the corresponding fragment of configuration memory. And again, the essential bits from this fragment can be sampled in a blind manner. So this approach manages to inject faults in a selected design component. However, it still provides very limited precision because the granularity of P blocks does not reach smallest design components. And in addition, this method is quite intrusive because it introduces area constraints which alter the place and root results. So instead, we propose a much more fine-grained approach. An approach that would allow to sample faults directly from the hierarchical netlist. So, assuming we could accurately locate essential bits of each cell in the netlist hierarchy, then the fault injector would be capable of selectively targeting any component in the design tree, regardless of its size and up to individual register or lookup table. And it would not require any placement constraints, so this means it would be low intrusive. Of course, mapping of essential bits is quite a complex problem, and to the best of our knowledge, up to this point there were no such bit-accurate fault injectors, at least in the public domain. So this slide illustrates the architecture of the bit-accurate fault injector that we propose in this work. It includes several modules on the host side and on FPGA board side. The host side comprises a set of Python modules. They are responsible for parsing the design, mapping essential bits, generating the fault load, controlling and monitoring the execution of experiments on the board side, and so on. The board side includes an FFI controller that coexists in the same chip with the design under test. The FFI controller is responsible for manipulating the content of configuration memory to inject and to remove faults, and in some cases also for supplying tests to the design under test, and also for analyzing the fault effects. In the case of plain FPGA, this FFI controller is represented by a microblaze processor, or it can be also represented by a hardwired ARM core in the case of a sync device. This FFI controller can be added to the custom FPGA design by means of a TCL script. This TCL script is available in the BAFFI repository. The resulting FPGA design with integrated FFI controller is then supplied to the input of the BAFFI tool, And another file provided on the input is an XML formatted configuration of a FRACTAL experiment. I will explain about this file on the next slides. So once the BAFFI tool is invoked, it first parses the design files. The debug bitstream and essential bits are parsed into a model of configuration memory. The hierarchical netlist and logic location files are translated into a netlist model. And then the mapper module locates essential bits of each cell from the hierarchical netlist. In essence, it calculates a set of configuration memory addresses, including frame, word, and bit offset. And this is based on custom mapping rules that we define experimentally for the lookup tables, registers, blockrams, and lootrams. All the mapping details can be found in our paper. The resulting design model is now used by the fault load generator to sample faults from the fault space. Faults are sampled attending to a set of filters that are defined in the configuration file. A dot scope specifies the name of the targeted design component where fault should be injected. A target logic filter allows to selectively target lookup tables, registers, blockrams, and lootrams, or the entire set of essential bits. So these two filters are required to set up the fine-grained FFI experiment. The chip area can also be constrained using the p-block filter. It can be combined with a hierarchy filter, or it can be used on its own to set up the area-based FFI experiment. In the statistical sampling mode, we can also adjust the required sample size and the sampling error threshold that should be reached to terminate the experiment. The fault multiplicity and injection time are also adjustable. The fault list is processed by the BAFFI sequencer. For each fault in the fault list, it executes several steps in a loop. Inject fault, run a workload on the design under test, trace the fault defect to determine the failure mode, remove the fault and recover the design under test to its initial state. The sequencer supports two alternative setups. The host controlled setup is used when we need a standard debugger on the host side. In this case, the on-chip FFI controller is only in charge of fault injection, but the design under test control and evaluation of fault defects is performed on the host. The board controlled setup is useful when the fault defect can be evaluated directly on chip. Then the on-chip FFI controller is in charge of both the fault injection and effect evaluation. The host only monitors the results reported by the FFI controller. And this setup reduces the injection latency, and it also has a faster runtime. And finally, BAFFI generates a fault injection report in several formats. And in addition, all the collected FFI results are exported to the SQLite dataset, and then we can query and visualize the results from the dataset using an interactive web interface. There is a number of filters to query the results and several widgets to visualize the distribution of failure modes, and also to highlight the weak points of the design, and also to check the details of each individual injection run. Then we propose two case studies to showcase the usefulness of BAFFI. The first case study analyzes fault sensitivity of the Noel 5 processor, which is prototyped on the Virtex UltraScale Plus FPGA. To test this CPU, we need a GRMON debugger on the host side, so we use the host controlled setup. We inject single-bit upsets in essential bits. First, following a common p-block approach, we target lookup tables and then the entire set of essential bits, including routing. So we can see an aggregated estimates for the CPU core as a whole, roughly 1% of silent data corruption and 2 to 3% of hangs, including crashes and timeouts. And also, thanks to the capability to selectively target different types of logic, we can see that routing is more sensitive than logic. Then we use bit-accurate hierarchical injection to obtain the detailed estimates for each component of CPU core. So we can see that the most critical CPU component is the integer pipeline. And among the pipeline stages, the most critical ones are the execute and the memory access. So this is the kind of results that can be obtained by BAFFI. In the second case study, we targeted 3 smaller processors, MC8051, AVR, and Microblaze. And we use BAFFI and a simulation-based fault injector from the Davos toolkit. The goal was to validate BAFFI results by simulation. The simulation results we obtained at 2 representation levels. At the register transfer level, targeting only the registers, and at the gate level, targeting all the netlist primitives, including the registers, lookup tables, and block RAMs. So, as we can see on these bar charts, in all cases, BAFFI results match the simulation results. At least the discrepancy never exceeds the sampling error. So, up to this point, we can see that BAFFI provides accurate and very fine-grained injection analysis. So it can almost replace the simulation-based injection in this sense. And especially considering that BAFFI is 2 to 4 orders of magnitude faster than the simulation-based fault injection. So we can see the exact estimation on this slide. Up to 80 times faster when targeting the registers, and up to 11,000 times faster when targeting the combinational logic. And if we compare the 0.5 runtime with other targets, we can see that the board control at FFI can be up to 20 times faster than the host control at FFI. But of course, these numbers are very application specific. So, in conclusion, the bit-accurate mapping of essential bits allows BAFFI to perform the very fine-grained fault injection experiments. And this is something that previously was only possible with a simulation-based fault injection. But now it can be also done in FPGA, and 2 to 4 orders of magnitude faster than in simulation. And this makes BAFFI very useful for verification of complex designs, like multi-core CPUs and systems on a chip. The bit accuracy of BAFFI is currently limited to the registers, the lookup tables, block RAMs, and loot RAMs. But in the future, we will extend the bit accurate support to the rest of FPGA resources. And finally, we have published BAFFI as an open source extension to the Davos toolkit. So you can find it under the link on this slide.